let's look at some second derivatives then. And those second derivatives, that could be then either two components of the same field, or, I mean, it could be sort of this kind of thing where I have two different components of the same field, or actually alpha and beta can be the same, so it's just a quadratic term, or it could be two different perturbations, like a magnetic nuclear moment and a magnetic field. And if and to make that sort of have the possibility that there are two different ones, then I have to evaluate that again for both fields being set to 0. And then with the same argument as before, the energy is expanded in 0th order plus 1st order plus 2nd order plus higher orders. The 0th order does not depend on the field, that's just a constant, so that goes out when I take a derivative. The 1st order correction is linear in the field, so if I take one derivative, as you can see, the field disappears, and if I then try to take a second derivative, I get 0. So the first contribution from where I can get something, that's the second order energy correction. And then if I afterwards set the fields all to 0, then all the higher order corrections disappear. But it's actually worthwhile to remember, if I wouldn't do that, I would have to have a 3rd order, 4th order and so forth energy correction term still there. But now we set them to 0, so this is actually just then the second derivative of the second energy correction in the presence of fields with respect to two fields or two components of a field. Right, and if I look then at my second order energy correction, I have this term, which includes one of those operators. So I get one of those operators. And again, I mean, this is an expectation value. So I have in a way the same story as I tried to tell you here. The only thing which in this term depends on the perturbation is the Hamiltonian, not the field. So I end up taking the second derivative of the Hamiltonian here. Like this. And then I come to this sum over states term. And again, if I look at that, the sum over states term, that consists now again not of expectation values but of transition moments. But again, the wave functions, they are unperturbed wave functions. So the wave functions don't depend on the perturbation. So the only thing which depends on the perturbation are those h's. Now, that story gets a bit longer because the first thing, if I take the derivative, I mean this is the first derivative, if I take the derivative with respect to f2 beta, and I mean this is a product of two transition moments, both of them depend on the field because both have a first order Hamiltonian. So I'm going to have to take the derivative of the first one and leave the second one unchanged. And then I take the derivative of the second one and leave the first one unchanged. So I get two terms taking the first derivative. And then I come with the second derivative, now with respect to f1 alpha. And the first term I had was I took the derivative of this one, But that is linear in the field, so there is no field dependence anymore left in that. So they are taking the second derivatives. I don't have the problem with the product rule any longer, because one of the two transition moments is already without a field. So I end up with having two terms, where I have taken the derivative of each of them. So how to write that? What do I want to write that? Yeah, I'll write it here. So I get a sum over n equals to 0, and then what did I say? I say I take this derivative of the first one first, so I get the derivative of h1 here with respect to f2 beta. So I see, oh, that was taking the first derivative, and let's make a nice parenthesis, and then I had a second term, and I mean the energies in the denominator, they are field independent, they are the unperturbed energy, so luckily there's nothing going on there. And as I'm using first derivative and using the product rule, then I get a second term where I took the derivative of this one. So I have psi n, that's n, sorry, psi n, and then the derivative of this Hamiltonian with respect to f2 beta, psi 0. That was taking the first derivative where, I mean, the other term I leave as it is. And then I have to take the second derivative, again a derivative of all that thing with respect to f1 alpha now. But this is the first order, so if you take a derivative, there's no field dependence anymore in it. So I am going to take now derivative of this one, so that's psi n. And now the derivative of this one with respect to f1 alpha, psi 0, and same story here, psi 0, derivative of this Hamiltonian with respect to f1 alpha, psi n. So I get two terms. And often the two terms are the same actually, because remember, if the functions are real, then taking the complex conjugate of the whole one just interchange the order of the Brown-Ket state, and then they might become the same. It depends a bit on what the operators are. And then I might get it sort of just twice.